Hello, everyone. It's a pleasure having you all joining us this evening. Tonight, we are welcoming Aditi Srivastava and Josh Hirakawa to give a tech talk on load balancers. Aditi, Josh, whenever you're ready, please take it away.
Thanks so much, Lucas, and thanks to everyone for being here today. And a special thanks to Remake for sponsoring this tech talk. Today we're talking about everything load balancers, from what they are to how they work and how they fit into the bigger picture of system design, as well as the algorithms that are used to define its main functionalities. Aditi, you had a really good analogy that describes on a high level what load balancers are, if you don't mind telling us about that.
Yeah, totally. So I want everyone to close their eyes and picture this. You're in a grocery store, you've done your shopping, and you're ready to check out. But when you walk into the checkout section, you realize that there is a massive line ahead of you, but there's only one cashier. Everyone's tired, everyone's annoyed, and they're just waiting to get on with their day. And the cashier is just looking so overwhelmed because no matter how fast they work, the line of customers just keeps on growing. Now, keep on closing your eyes and imagine this. Now there's three cashiers, and there's someone at the front of the line who's telling customers which line to go to. Which cashier to go to. The line is getting shorter, people are getting through faster, and everyone is chiller and happier. So that person at the front who's telling people where to go, that's what a load balancer is. Okay, you can open your eyes now. Thanks. So yeah, it's not the person who's checking out your groceries, but it is the person who's making sure that the workload of customers gets spread fairly across all the cashiers. So yeah, that's basically what load balancers are in a nutshell. They are the people who kind of direct the traffic in system design. They decide where each incoming request goes. And instead of just dumping all of the traffic onto one server and crossing your fingers, they distribute requests across multiple servers. And this helps apps a lot because it keeps your system available. Because if one server crashes, and load balancers can ensure that there's another one that can take the other server's place. It also makes apps more scalable because it helps distribute load to servers as network traffic grows. It also improves app performance because it reduces response times by making sure that no one server is overloaded with requests. And it also acts as a central entry point in case you want your app to do things like authentication or verification or security checks. Load balancers help act as that one centralized authentication point. So in short, it makes everything smoother, faster, and more reliable. So load balancers actually sit between the users and your backend. When a request comes in, a load balancer doesn't just randomly assign it, it actually uses smart rules and health checks to decide which servers are healthy, available, and ready to respond. They do this all in real time without the user ever noticing anything. But honestly, to really understand how smart a load balancer can be, we have to kind of zoom out and look at where it sits in this whole internet stack. So for that, I'm going to hand it over to Josh, who is going to walk us through what is called the OSI model, aka the seven-layer cake of the internet, as we like to call it.
Thanks, Aditi. Yes, so the OSI model or the Open Systems Interconnection model, it's a conceptual model. So it represents how two devices can communicate with each other over a network. So we have a layer one being the physical layer. We like to imagine hardwares, right, communicating through cables, switches, electrical signals. And as we ascend through the layers, it just develops in complexity. And so layer seven would be the application layer. We like to think software at this point. Load balancers, they operate on layer four, the transport layer, and layer seven, the application layer. So let's just talk about some differences between the two. Layer four load balancers, the transport layer, can understand, like read IP address and port, understand TCP level. So this means that if you got a request, they're not going to be inspecting the contents of that request. It's just kind of guiding, checking the IP address and seeing the destination port, sending, redirecting requests. This makes it very low latency and efficient. On the other hand, we have a layer 7 load balancer, which application layer understands HTTP and HTTPS. This means these load balancers can take a request and look at the actual request content, like the URL, headers, and cookies. This allows for smarter decisions when routing. This allows for testing methods like canary deployments and A/B testing, but overall, just higher latency because of the complex computations. It's really important to note that layer four and layer seven load balancers, it's not like one or the other within a system. you can have both of them exist in different areas depending on the requirements or the needs of that specific position in the system. Aditi, so when we think like load balancers are processing all the network traffic through, right, this one point, doesn't that technically mean we're creating a bottleneck or like a single point of failure?
That's a great question, Josh. And my answer would be, nah, don't worry about it. And the reason why is because we have actually some really good strategies to prevent that scenario from happening. So one strategy is called the active passive strategy, where we have one active load balancer that's handling all of this traffic, and then we have a passive one that's on standby. So there's not really a single point of failure because if the active load balancer fails, the passive one can just take over. We also have the active strategy, which is where we have two active load balancers that are live and they're sharing a shared cache, so they're sharing the same memory. And if one active one fails, the other one can just handle all of that load. But this does put more pressure on that one remaining load balancer to do all of that work, and that's definitely a trade-off that should be considered. Honestly, in real life, you'd probably see the active passive strategy with load balancers more often. But yeah, if you combine that with the health checks that load balancers do and the automatic failover, aka having a standby as backup, then you're creating a system that has a lot of fault tolerance, aka reliability in terms of making sure that a system is continuing even though failure happens. Okay, so Josh, you know how earlier we were talking about how load balancers kind of made smart decisions in handling network traffic? So I think there's like static algorithms, which is basically using fixed sets of rules to decide how to handle traffic, and then dynamic algorithms, which kind of uses real life information and adjusts and adapts in real time. Did I get that right?
Exactly. Yeah, absolutely. And we as developers hear the term static and dynamic very often. Well, when we talk about load balancing algorithms, they're divided into these two categories. Static would be using a predetermined set of rules or a pattern, and then dynamic will be retrieving more real-time data to analyze and determine where to send that request. And so let's just talk about a few algorithms, starting with static. We have round robin, weighted round robin, and IP hash. We're going to start with round robin, and this one's a very simple one and widely used. And the best way to describe this is just to imagine dealing a deck of cards, right? Like, of course, you want to distribute all the cards evenly amongst all the players. That's essentially what's happening with round robin. Now, there is a weighted version. So when we say there's a weighted version of an algorithm, we're saying that now the load balancer is taking into account the vertical capacity of each server, meaning like, oh, how many requests can they handle? How much network traffic are they able to handle? And so we assign a weight to them. And this kind of offers improved performance and optimized resource utilization.
Wait, Josh. Okay, no shade, but it kind of seems like the weighted round robin strategy is a lot better than the regular round robin strategy. So how come companies don't just use weighted round robin like all the time?
Yeah, I totally get that. I totally see that. But here's the thing, as developers, we need to talk about trade-offs, right? Weighted round robin can do so much more in terms of functionalities because now we're thinking about how much load the server can handle. But this requires complex configuration as well as weight tuning, which is the process of adjusting weights. So if you scale the server, increase their capacity, you have to adjust that within the load balancer as well. So that's weight tuning, requires some labor intensive work. While the round robin doesn't require any maintenance, really, it's just a static algorithm. And so in that sense, we have to think about where we want to implement this. Round robin's perfect for systems that have consistent response times because you don't have to think about the amount of computations necessary for each request.
Gotcha.
And now that leads me to IP hash. This is a great algorithm because we're taking the client's IP address to determine which server to send that request to. This is a great one. We've probably seen this, experienced this as clients ourselves. But for every IP, we have the same server, which means we're providing some consistency in the system. Also, we're assigning servers that are close in proximity, so faster response times, right? So amazing algorithm here. That kind of leads me to the discussion about dynamic algorithms. Dynamic algorithms are awesome because now we're fetching real-time data. Let's talk about least connections and weighted least connections. So as the name suggests, so this algorithm is taking the number of active connections for each server and then determining which one has the least and then just sending all the network traffic to the one with least connections. So in this visual, we see that server one has 10 connections. And so we're just going to send all the network traffic until it hits about 100 connections. And then it's going to balance and distribute evenly among server 1 and 2.
Wait, hold on. This is like such a brilliant strategy because we're actually taking into account like each server's capacity before making that routing decision. That's like amazing.
Not quite. It's not capacity. It's actually the number of connections. And so this is a problem, right? Imagine if a server 1 was weak, if it was a little weak boy, right? Like we can overload that server so easily just because we're sending all the network traffic solely based on the connection count. This is why we have a weighted least connections algorithm. And now we're taking into consideration how much weight each server has, how much network traffic it can handle. In this visual down here, we see that we're sending 3 requests to server 3. And when it hits about 13 connections, it's going to start sending one to server 2, balancing it out. But imagine if it just keeps going. When it hits about 400 connections in server 2 and 3, it's actually going to start sending connections to server 1 because it's capable of handling 2.5 times the amount of network traffic. That's how it works. And of course, there's trade-offs to these, right? Crazy amount of configurations and monitoring required for weighted least connections for the weight as well as the number of connections. And for least connections, it's way easier to implement. You're only keeping track of connections. And it's, again, just like the round robin algorithms, really good for areas where you know you have consistent response times. This leads me to the last algorithm, which is the least response time algorithm. And now we're kind of taking the average response time for each server. It's a great algorithm, but it's very expensive. We can imagine that sending network traffic to the fastest server is awesome for the users. It's very user-facing and maximizes speed. But it requires so much resources and monitoring to be able to provide an accurate analysis of an average response time. And this is why bigger companies like Google and Amazon can implement an algorithm like this, oftentimes in the form of hardware. But that kind of sums it up for the algorithms. Aditi, I really want to know a little bit about some real life tools, load balancing tools that are used today by developers.
Yeah, totally. So we definitely have our pick to choose from. It honestly just depends on like what your stack is and what your use case is because they have slightly different strengths. So to start us off, there's Nginx, which is a super popular one because it's lightweight and you can honestly use it in like a variety of apps. There's also HA Proxy, which is known for being super fast and customizable, especially if you're like in an enterprise type startup, or if you just know that your app is getting a lot of traffic, then you can't really go wrong with HA Proxy. If you're working with the cloud, though, then Amazon Web Services Elastic Load Balancer is super convenient because it basically just like handles all of the load balancing logic for you. You kind of only have to set it up once, and then it just kind of takes care of it from there. It auto scales with your app, which is also really convenient, and it even layers seamlessly with like the whole layer 4 and layer 7 routes that we talked about previously in the OSI model. If you're working with containers, then you're probably going to come across the Kubernetes ingress, which is basically like a load balancer that sits at the edge of your cluster and it routes traffic internally to the right service in your container. So yeah, if you're going, whether you're hosting your own site, if you're working for a huge business, or you're going to go use the cloud, there is a load balancing tool out there that can meet your needs. So we wanted to add one last note before we wrap this up. So we are not really supposed to notice load balancers until something goes wrong, of course. Then they're pretty much the only thing that matters. Because when load balancers stop working, the app will go down, pages will not load, your users will be frustrated, and your team will be trying to figure out why one server is getting all the requests while the other ones are just sitting on their butts and not doing anything. So yeah, load balancers are designed to be the unsung heroes that work behind the scenes because when they're working, everything is smooth and fast, but they're pretty much one of the most critical parts of modern software infrastructure. They quietly keep your system online, your traffic balanced, and your apps actually scalable. And on that note, I'm going to pass it off to Josh to bring us home and close us out.
Thanks so much, Aditi. Yeah, amazing. And just to recap, load balancers are a crucial component in system design, right? Responsible for distributing network traffic to healthy servers and responsibly. This provides high availability, scalability, and performance. We know that we have static and dynamic algorithms that define its functionalities. But all in all, load balancers are just so essential for providing fault-tolerant modern systems. And so if you're a developer who's building, I highly recommend you or encourage you to just look more into load balancers because they're going to provide that level of optimization for your systems. Here are some resources to get you started. And once again, just want to thank Remake for sponsoring this tech talk. And I promise you, you'll never look at grocery store lines the same ever again. Thanks, guys.
Thank you, Aditi, Josh, for that tech talk on load balancers. I really appreciate how you also answered some of the questions that I'm sure most of us had as you were presenting these concepts and algorithms. And yeah, thank you everyone for coming tonight.